How many of you guys dream about going to space? Well, I know that I do quite a lot, maybe a bit too often. But if you've gone to space, you then sometimes have to come back again. I know Elon Musk probably wouldn't agree with me, but this can sometimes be the difficult part. So now if you're trying to come back from space, you've got to picture yourself sitting in this little conical capsule, plummeting through the Earth's atmosphere at Mach 15 or whatever it is. And if it was me doing this, I'd be looking out the window at this superheated plasma sheath all around me and really hoping that the guys in NASA had done really good simulations to make sure that the heat shield wasn't going to fail. Unfortunately, the simulations I would really like them to be able to do, super high fidelity simulations where you really understand what's going on at the microscopic level, are currently astronomically expensive to run, ironically. So in my DPhil research, I am working on using machine learning to accelerate these calculations so you guys, future astronauts, can be safe on your return to Earth. To be a bit more specific about the science, in these high atmosphere conditions, you can't use Navier-Stokes equations of fluid dynamics. The gas is too rarefied and you're traveling too quickly. So we basically instead imagine that we're dealing with a bunch of particles flying around in some simulation box. And in order to calculate the heating of the heat shield, we'll just count how many particles bump into the box, the sides of the box, and with what energy do they do that collision. And it turns out that this answer is actually going to be extremely sensitive to the details of how the molecules collide with each other. So there's two ways of resolving these collisions. One, you can do kind of a simple phenomenological model where you have some parameters which are calibrated to experiments. And these experiments were done in the 60s, and they had big error bars back then. Or you can do a big molecular dynamics type simulation where you really resolve the trajectory during the collision of two molecules, with an example in my bottom left picture of two nitrogen molecules colliding and exchanging some rotational energy. So I'd like to be able to do this, but doing this trajectory calculation is around 1,000 times more expensive than just picking a random number with some parameters. So given that we have these really expensive simulations that we'd like to be able to do, this is just a conditional density estimation problem of the output distribution of this collision given the pre-collision state. So I'm using machine learning methods like the mixture density network that you see in the bottom right to calculate these much faster. And indeed, we see in some simple cases that we can get 10 times speed up with the same accuracy. So it's the first step on the journey to making these simulations really, really fast and for you guys to be safe next time. Thank you.
I want to talk to you about the Barnes ice cap in the Canadian Arctic. It's collapsing and will cease to exist within the next 300 years, and we know this is because of climate change. Why is this a math problem, and why should you care about it? I'll prove to you that with a pretty simple mathematical model, we can actually isolate the collapse mechanism of this ice cap. For this, we need three ingredients. The first one is your model. We're going to assume ice is actually a fluid. Sounds counterintuitive? Well, on long time scales, ice actually behaves like a highly viscous non-Newtonian fluid. And that's yet to the nice model that you see here, kind of where ice spreads out as a thin film, so it's very wide, not very high. This gives you a nice PDE for the ice thickness, where the margin evolves freely. The second thing you need is a source term. So we need to understand how this ice cap grows or loses mass. How does that work? Well, the most important thing is it depends on the height that you're at. So the higher you are at your ice cap, the higher your altitude, the colder your temperature, thus you get accumulation rather than ablation that you get on the side. Crucially, the second ingredient, the mass balance here, also depends on climate forcing. So if your temperature is higher, you're going to get a higher surface temperature, thus more melting, thus ablation. Cool. The third ingredient that you need then is kind of a reference temperature state. We need to have a reference for what this ice cap actually looks like in nature, and this is data. So I dug into some data from the 1970s to 1984 that gives us a really nice layout of what this ice cap actually historically looked like. That's great. That sets you up with the model. But what does the math then actually tell you? The model that we set up actually doesn't admit a steady state. Does this mean it's complete garbage? No, because it still gives you a separatrix between unbounded growth and collapse. And so the question then becomes, where does Barnes sit relative to that? So does it grow unboundedly or does it collapse? The central result of my thesis is that even in the 1970s, so the data that we start from, we need a climate forcing of minus 0.01 degrees Celsius in order for Barnes ice cap to survive. This means you need cooling and a temperature colder than what we had back then, which we know is now far away from what global temperatures are today. The point here being that even at the temperatures back then, Barnes ice cap cannot sustain itself between 2,000 years for the simulations that I run. Why should you care about this? Well, because the larger point this model is making is about irreversibility. From the mass balance that we looked at, you understand that altitude kind of forces how much melting versus how much freezing you get. And so as soon as you're below a certain height, you're never going to be able to get back. So there's a tipping point, and kind of the things that you hear in the news, actually, that's just mathematics. The larger point of the thesis being that like so many of the big problems that we have in humanity, most of them are just simple math. Thank you.
Good afternoon. Today I'll talk about my fourth-year master's thesis on parameter-free accelerated gradient descent. Optimization algorithms are the workhorse of modern machine learning. A central question in optimization theory is the characterization of an algorithm's evaluation complexity. Given an objective function f that is potentially non-convex but bounded below, we're interested in computing a point x such that the gradient norm is less than or equal to epsilon. And we want to measure the number of gradient oracle calls which we require in order to compute this point. So for smooth functions, classical theory for steepest descent requires 1 over epsilon squared iterations. And this is the best known rate, and it's tight for first order methods. The seminal work by Carmona and others accelerate this rate to 1 over epsilon to the 5 over 3 through exploiting higher order smoothness, and this is currently the best known rate for first order methods, even under higher order smoothness. However, a key limitation of their algorithm is that they require a priori knowledge of problem smoothness constants to calibrate their step sizes and momentum. These constants are rarely known and difficult to estimate in practice. Those of you who are familiar with SGD or ADAM know that we need to tune the learning rate. And in practice, using a fixed step size is often too conservative as we are unable to adapt to local curvature. And also, their theoretically specified algorithm can be up to 40 times more costly than a practical variant, which they run in their paper, but no longer carries the stated convergence guarantees. So we introduced PFAGD, which is a deterministic parameter-free first-order algorithm. And a central obstacle in Nesterov acceleration is that there's a tight coupling between step sizes and momentum, and we circumvent this using two key ideas. Firstly is using backtracking to adaptively estimate the local curvature, and the second is to recalibrate momentum using restarts when acceleration stalls. Both of these use only first-order information. So we basically prove that our algorithm is able to achieve the optimal rate of epsilon to the minus 5 over 3 in a parameter-free fashion, so there's no need to know any problem constants. The bound is also independent of the problem dimension, making it suitable for problems where D may be large. And PFAGD is, in practice, implemented faithful to theory. In practice, we consistently outperform other practical variants of accelerated algorithms, and we are a viable alternative to nonlinear CG, which is the state-of-the-art class of algorithms for non-convex optimization. And nonlinear CG has historically lacked convergence guarantees, and this is a direction for future research. To conclude, PFAGD is practical to run, theoretically optimal, and empirically robust. Thank you for your attention.
So my research focuses on accelerating sequences of eigenvalue problems using subspace recycling and row subsampling. Now, if this title scares you, well, don't worry, because you're looking at a very, very simplified version of this problem in this slide behind me. Now, imagine you have a series of visual mysteries identifying a person and their accessory in a sequence of images. You're given a hint, which is the images are similar to one another, but there is a catch. Looking at the entire image and trying to extract this information is very, very expensive. Now, as you are a smart audience, you have already identified who's the person in the images, but let's assume it's not that easy. Now, I listed here 3 possible strategies. The first one, you look at each image independently, which is, of course, very expensive. A second one, which uses the hint, You remember the solution of the past problems, and you quickly check if the person or the accessory in the new image is similar to something that has already appeared before. The drawback of this strategy is that you still have to look at the entire image. And then there is a third strategy, which is our strategy, and we combine this recycle of information with a smart cropping technique. So we not only remember the solutions of the past problems, but we also remember the location of the information. So if we see glasses, we remember the area around the eyes. If we see hats, we remember the area above the head. And thanks to this, we can solve the problems without scanning the entire image. Now, why is this problem related to my research? Well, if you think about this, an image is seen by a computer as a grid of pixels, and each pixel is a number, so an image is seen as a matrix. And then you can think about the information about the person or the accessory as encoded in one specific vector, which is called leading eigenvector of the matrix. And what about the past solutions that we carry forward? Well, they're just a set of vectors, so a subspace. And what about the smart cropping technique? Well, this is just a row selection method for the matrix. And why do we care about speeding up this sequence of problems? Well, because the matrices we want to analyze in practice are far more complicated than a picture of me wearing a Mario hat. So they may, for example, come from the numerical simulation of a physical system, or the monitoring of a network during time, or each of these matrices may encode the feature of an AI model at each step of its training. And thanks to our new strategy, we are able to solve these difficult and crucial problems very, very fast. Thank you.
Hey everyone, I'm Julius, and today I want to talk to you guys about percolation. Percolation is a probabilistic model first introduced to model the behavior of fluid passing through a porous material, like hot water percolating through coffee grounds. In my thesis, I aim to take results that we know about a simpler, discrete, classical model called Bernoulli percolation and extend them to a continuous, newer, more complicated model called Gaussian percolation. Bernoulli percolation is defined like this. Take an infinite graph of edges and vertices and flip a coin. With probability p, the coin lands on heads, and if it does so, then we open an edge to let fluid pass through. The main question is this. As we vary this probability p, what's the likelihood that water is able to flow through an infinitely large cluster of open edges? It turns out that this model exhibits what we know as a phase transition. For small p, most of the edges are closed, and so all of the clusters will be small and finite, whereas for large p, most of the edges would be open, and so we'll see an infinitely large cluster with probability 1. Now, it turns out that there's, importantly, a critical probability where as we pass from the subcritical to the supercritical regime, there's a single critical probability where this behavior changes suddenly. Meanwhile, for Gaussian percolation, this is defined on objects called Gaussian fields. Think of these like a random landscape, where the height at each point is normally, or Gaussian, distributed. If we take a landscape and submerge everything below a certain fixed height underwater, then we end up with a configuration of lakes and islands. And it turns out that as we vary this height as well, we'll also see a phase transition in the size of these islands. There's a subcritical regime where islands are small, a supercritical regime with an infinitely large island, and a critical regime exactly in the middle. Yeah, but the similarities extend far beyond the phase transition, the existence of the phase transition. It's conjectured that for any result we can say about Bernoulli percolation, we should also be able to say this about Gaussian percolation. And my thesis takes some of these results and extends them to the Gaussian case. The holy grail of this field would be to say something about the scaling limits of interfaces for these models. It turns out that it's incredibly difficult to say something about this. This is, if we look at the critical region and we zoom out more and more, what can we say about the coastlines between the islands and the lakes? Even for Bernoulli percolation, it's incredibly difficult to say anything about this. But the hope is that one day we'll be able to show universality for both Bernoulli and Gaussian percolation models and show that the same scaling limit exists for any Bernoulli percolation model and any Gaussian percolation model. Thank you.
So if I exercise an hour a day, what will happen? If I don't want to catch a certain disease, what should I change in my lifestyle? Or should I take a certain drug or not? This is a kind of quorum-causal inference is answering. And that correlation cannot tell us because it's merely relationship between two things. It's a much stronger statement than that. And the gold standard is randomized experiments. We fix our covariates, our confounders, and then we randomize our exposure, and then we get a good causal effect. However, randomized experiments are either too expensive, it's unethical to force someone to smoke to see whether they get lung cancer, or it's just impossible to let a government to implement only one policy in 10 years to see how it goes. So what we have got is what have observed from the past. However, how do we still deal with this unmeasured confounders that we can adjust for? Well, we use instrumental variables. Is variable going into our exposure x and only for x going into our outcome y. In other words, there's no path from the instrument set to y directly. So we are done. Well, a practitioner will disagree with you. He will say, now I've got 100 instruments, claimed to be instruments. I've only, an idea that maybe, more than half of them are true. And now I get, various different estimates, and I don't know which one to trust. If I just aggregate them, I get a really poor estimate. So we're kind of back to square one. And so what should we do? So now our method is have Pareto guarantees that is consistent when sample size is increasing to infinity. It has fast convergence that when we have finite sample, it's very good. It's computationally efficient, and also it's very easy to implement for a practitioner. So how do we do it? When we say more than half of the instruments are true, the median is quite reliable. So we can look at each of the individual estimates, look at the distance between itself and the median, scaling it with the variance, and then we do a downward testing procedure. They throw away the one with the biggest deviation, and so on. We carry on until our test does not reject, and we stop with a set of good estimates of we selected a good set of instruments. So now reliable causal effect is definitely possible, even when we cannot do randomized trials, and even if we have imperfect instruments. And we have the good Pareto guarantees and also practical advantages with this method. Thank you very much.
So since the last century, formalization of mathematics has caught a lot of attention. The ironclad version of this is obviously Hilbert's program, but it's false. And the softer approaches continue to make progress, and more often the first step is to think about the axiomatization of a class of structures of interest. As a warm-up, recall from set theory that the class of sets is axiomatizable from ZFC axioms. Now, to think like a logician, the next question you may be interested is in whether subclasses are axiomatizable, in our case, of infinite or finite structures. And as spoiled on the slide, we know that infinite structures is axiomatizable, whereas finite structures are not, due to compactness. The remedy here is to look at pseudo-finite structures, which are ultra-products of finite structures. They satisfy the same first-order sentences that finite structures do, and also allow for more elegant axiomatization. In my master's dissertation, I'm concerned with resolving a similar obstacle born from non-axiomatizability, but from functional analysis. So now to describe metric structures in the first place, we need to add some continuity to our language. The discreteness of the usual logic that we work with is due to the truth value being binary, 0 or 1, or false and true in the natural language. But there's a sense that this truth function could be seen as continuous, which is to equip the natural numbers or any domain set with the discrete metric. And we can take this one step further, which is to take our domain not as a set, but as a metric space. And the truth value is then taken on a closed interval from 0 to 1, function and predicate symbols being continuous, uniformly bounded functions, and quantifiers being infimum and the supremum functions. Now we're prepared to think about the logic access to metric structures. To begin with, we know that metric spaces are axiomatizable because now with this distant predicate, we can write down sentences like defining properties like triangular inequalities. For C-star algebras, which are to be thought of as some special classes of Banach spaces, Farahart and Sherman also proved that they are axiomatizable from 10 axioms. They're both interesting as mathematical objects and as a rigorous framework to quantum mechanics. However, many subclasses of C-star algebras is not. And in my dissertation, the interesting adjectives that I worked with is more and more generalized notion of this finite dimensionalness. To see this result, we look at some ultra powers again. For locally finite dimensional, locally matricial things, we look at M to infinity, which is the Carr algebra, and look at its ultra product. And for nuclear algebras, we look at the Quin's algebra. In any case, we see that the ultra powers are not in the original subclass. Right. Essentially, to solve this problem, which is that being somewhat finite is not perfectly described by some theory, we can either change the finiteness or we can change the theory. And with the continuous theory, we have a way to use a family of uniform functions to approximate the axioms that we're working with, which get us to an approximate axiomatizability. This pattern from non-axiomatization to approximate axiomatizability gives logic access to more subclasses than I've described here, and is a general pattern for a lot of subclasses. Thank you.